All right, let's try a little thought experiment. What if I told you the universe isn't, well, empty? Forget the void. Instead, picture this: a gigantic container filled to the brim with something a lot like sand, packed so incredibly tight that it starts to behave in ways that just, well, they defy common sense. Sounds pretty out there, right? But that's the wild starting point for a theory of reality we're going to unpack today.
No, really? Let that sink in for a second. Everything we've ever learned tells us that space is emptiness, right? It's the void. We fly spacecraft through it, light zips across it for billions of years. But what if that's all just a big illusion? What if at the most fundamental level you can imagine, space itself is actually a solid? I mean, how could that even work? How could you build a universe on top of something like that? And okay, just when you think your brain can't twist any further, what if that same solid space could also flow like a liquid? I know, it sounds impossible, but that's the central paradox this whole theory is built to solve. This idea of a universe that's somehow both totally rigid and completely fluid all at the same time. It's like it's balanced on a razor's edge between the two states.
Okay, so how do we even start to make sense of that? Well, the key, the absolute cornerstone of this whole thing, is a concept called the jammed vacuum. It's exactly what it sounds like. It's the idea that the fabric of space itself is perpetually stuck, or, well, jammed. And believe it or not, you've actually seen this happen. It's called a jamming transition. Just picture pouring sand or even coffee beans into a jar. At first, they flow, kind of like a liquid, right? But then you give the jar a few taps, you pack them in, and bam! They just lock up. They become solid. That exact moment, that tipping point, is what scientists call the J point. And here's the absolute kicker. This theory claims that the entire vacuum of space exists exactly at that critical point. It's always perpetually on the verge of flowing, but held perfectly, rigidly in place. And this isn't just some vague idea. This is where it gets really, really specific. See, this jamming point isn't random at all. It happens when each little grain of this cosmic sand is touching a very particular number of its neighbors. It's almost like a magic number for the universe. And that number? It's about 14.4. So what on earth does that number, 14.4, even mean? Well, it represents the average number of contact points, or neighbors, that each particle has in what physicists call a random close packing. Think of it like this. It's the absolute densest you can possibly cram a bunch of random spheres together without them snapping into a perfect, neat crystal structure. It's the point of maximum chaos, maximum density. And this theory says, yep, that's our universe. Okay, but that brings up a massive question, right? How could the universe possibly maintain such a delicate, perfect balance? I mean, shouldn't it just collapse one way or the other? Well, the answer comes from this really cool idea called self-organized criticality. The classic example is a sand pile. You keep dropping grains of sand, one by one. The pile grows, and the slopes get steeper and steeper, right up until they're at the absolute maximum angle possible before an avalanche. The pile organizes itself to be in a constant state of almost avalanche. And the idea here is that the vacuum does the very same thing. It naturally fine-tunes itself to stay in that perfectly jammed critical state. All right, so let's recap. We've got our medium, this jammed vacuum, this cosmic sand. But now for the really big question. Where do the forces of nature come from? You know, things like gravity? Well, in this model, they aren't some mysterious, invisible fields. Nope. They're just these straight-up physical, mechanical consequences of messing with this cosmic sand. And it all starts with this weird, counterintuitive property of granular stuff called dilatancy. You've seen this. Think about walking on wet sand at the beach. You put your foot down and what happens? The sand right around your foot actually looks like it gets drier, doesn't it? That's because your weight is forcing the grains of sand to shift and ride up and over each other. And to do that, they have to spread out, which makes the whole thing expand in volume. It feels wrong, but it's a very real effect. And here is the incredible reveal. In this model, that's gravity. Mass doesn't create some magical force field. It just pushes on the vacuum around it. It shears it. That forces the local grains of space to do that same thing, to ride up and over each other, causing space itself to expand just a tiny bit. And that local expansion, that little pocket of lower density, that is what we perceive as the pull of gravity. It's not a fundamental force. It's just mechanics. But that's not all this medium can do, not by a long shot. Think about pressing down on a pile of sand again. The force doesn't just spread out evenly like it would in water. Instead, it gets funneled along these super narrow, almost invisible lines called force chains.
They act like a hidden internal skeleton inside the pile, and they carry almost all of the stress. And you can probably guess what's coming next. According to this model, those force chains are the strong nuclear force. Yeah, that unbelievable power that binds protons and neutrons together inside an atom's nucleus. In this picture, it's nothing more than a direct, physical line of tension transmitted from one grain of space to the next. I mean, just stop and appreciate how elegant that is for a second. You have one single underlying substance, this jammed vacuum, and from it, you get two completely different fundamental forces. Gravity comes from this large-scale change in volume, that's dilantancy. The strong force, on the other hand, comes from this direct one-dimensional line of tension, the force chains. It's incredible. Two forces, one medium. So we've spent all this time talking about the grains of space, the solid bits, but what about the empty spaces in between them? Well, it turns out the nothing is just as important as the something. These gaps form what the theory calls the network of voids. Now, don't think of this as just dead space. This isn't passive nothingness. A better way to picture it is like the network of channels inside a sponge. It's a continuous, interconnected web that runs through the entire structure. And in this theory, this void network is an active medium, all on its own, with its own unique and crucial properties. Okay, fair warning. The physics used to describe this gets pretty heavy. It uses something called a Cosserat's continuum. But don't worry about the fancy name. All you need to remember is this one key detail. It means every point in this void network can do more than just move around. It can also rotate independently. It can have its own local spin, kind of like a tiny microscopic whirlpool. And that ability to spin is everything. This is basically the decoder ring for where electromagnetism comes from. So you get these twisting waves propagating through that void network? Well, that's what we experience as an electric field. And the local spin of the voids themselves, those little whirlpools, that's what we experience as a magnetic field. All of a sudden, electromagnetism isn't some abstract weird force anymore. It's a purely mechanical property of the gaps between the grains of space. So, I mean, this is a pretty beautiful and comprehensive picture, right? But any good scientific theory has to do more than just sound neat. It has to actually predict things or explain things we see in the real world. So the big question is, can this granular model actually solve any real-life cosmic puzzles? Well, let's take a look at a couple of places where it just might. Let's start with something simple. Ferromagnetism. You know, the force in a regular old fridge magnet? Where does that powerful, persistent magnetism come from? This model has an answer. It's called nematic jamming. Just imagine all those tiny whirlpools spinning away in the void network. Now, what if, in a certain material, they all decided to align and spin in the same direction? When you get billions and billions of them lined up, their tiny individual magnetic fields add up to create one big, powerful, coherent magnetic field that's strong enough to stick to your fridge. Okay, this next one, this might be the wildest prediction of the whole theory. It allows for something called vacuum triboluminescence. It basically says that if you put space itself under enough stress, or talking the kind of insane gravitational forces you'd find near a supermassive black hole, the granular lattice of the vacuum can literally fracture. It can crack. And when it does, it releases a flash of energy in the form of light. And this isn't just a cool idea. It could be a real mechanical explanation for a very real mystery, a strange excess of high-energy gamma rays that astronomers see coming from the center of our galaxy. So after all that, where are we? What this all points to is a fundamental rethinking of what our universe is. It suggests that reality itself isn't smooth and continuous, but that it's, well, granular. Let's just pull back for a second and look at the big picture one last time. Look, when you boil it all down, it really comes down to just a few key ideas. First, the vacuum of space isn't empty, it's a jammed granular material. Second, from the solid grains of this material, you get the purely mechanical effects that we call gravity and the strong nuclear force. Third, from the voids or gaps between those grains, you get electromagnetism. And finally, when you put it all together, this completely mechanical view of the universe might just give us real physical answers to some of our biggest cosmic puzzles. You know, it's such a radical departure from how we usually think about physics. It reframes the universe not as an empty stage where particles are the actors, but as a dynamic physical medium that is itself a critical part of the show. And it really leaves you with one last mind-bending question to chew on. If space can jam, if it can expand, if it can even fracture, what else is it capable of?